Good. Thank you very much for the kind introduction. Thank you for coming, even after your big lunch. I hope you can stay awake. So in this course, which is 15 hours, so it's a lot of work, we're going to cover many different things. But I thought I'd start by trying to cover the big picture. But before I do that, I just wanted to thank people. Many people gave me some of the slides that I'm going to show you, all listed here. And also, I didn't list them all, but many of my graduate students, postdocs, and former members of my group also gave me some of the slides I'm going to show. So we live in a rapidly changing world, and a big problem we have is energy. We have a lot of people in the world don't have the energy they need to live at a high standard of living. And the rest of us have kind of more energy than we need, and we're kind of wasting it and polluting the atmosphere. And in particular, most of our energy system is based on burning fossil fuels, and that's emitting a tremendous amount of carbon dioxide into the atmosphere. And that's the main cause of the greenhouse effect, leading to warmer temperatures, maybe including the temperatures you're feeling outside today here in Princeton. I'm coming from Boston. Boston, we have a section, used to be called the Seaport District, now called the Innovation District. But the people who work there call it the Inundation District, because every time there's a high tide now, the ocean comes up and it floods all the streets there. And it comes up through the storm sewer system, because this, even if you have a dike to block the ocean from going directly into the land, the storm sewers are emptying into the ocean, but when the ocean level gets above the outlets, then the water can come back up. And so this manhole covers come up, and the ocean water just comes and fills the streets. And this kind of thing is also happening quite a lot in Norfolk, Virginia area, and is predicted to happen a lot in Florida coming soon. And that's just the US point of view. There's many other countries in the world that have been suffering this kind of problem for a long time. Bangladesh is one that's kind of famous for this problem. I just read that one of the islands in Panama, they just evacuated everybody who lived on it because now it's getting so close to the sea level that if they have one storm, that the ocean might just completely cover the whole island and wash away all the houses. So they built a whole new town on the mainland and made everybody leave the island. And all of this, that's all caused by the global warming. It's melting the ice caps, melting the glaciers, and just the thermal expansion of the ocean water is making the ocean rise up. And so a big part of this, as I said, is due to the fossil fuels, which are the main things we're combusting when we study combustion science. And so it's very important for all of us engaged in this activity to really understand the big picture. So we have to figure out how are we going to switch to a system that has less of a greenhouse impact than our current system. And so there's a lot of ideas for this. I'm sure you've heard about hydrogen and e-fuels and biomass and biofuels. And maybe some of you have also heard about ammonia and different kinds of metals, all kinds of ideas about what you could use as the energy carriers and what you could use as the primary energy sources to power the society, to provide all the goods that we want. And they really are good, the goods that we have. For example, I drove down here with my wife from Boston. It's extremely convenient to drive in a car compared to like 200 years ago, people would have taken a horse. It would have taken 3 weeks to get here. And my butt would be really sore, but instead I just comfortably rode in my nice air-conditioned car. It was really great, right? So that's really an advance, and we don't want to lose that advance, but we have to change something in order to solve the climate problem. We have these questions like, what sectors does combustion have a role to play? And basically, it's everything, all the sectors. So almost our entire economy is driven by fossil fuels now. And so everything has to change. This is a great for employment for you guys, because over the next, say, 40, 50 years, almost everything in the whole of how society works and civilization works is going to have to change. All the mechanical stuff, all the sources of energy, all the chemicals industry is going to have to change. And it means you have to be all re-engineered. Because when it was engineered the first time in the 19th and 20th centuries, people were not aware that the greenhouse effect was really a significant thing that you had to worry about. And so it didn't come into the calculations when they were doing the designs. But now we know that it's really important. And all the countries in the world in the Paris Agreement have recognized that it's important. And so now we have to figure out, we engineers have to figure out the solutions for society to allow society to deal with the problem. We also have old problems. We have problems like fire. So almost every town in the United States has a fire company, people whose job full-time is to sit around and be ready to put out fires, because fires happen so often and are so devastating that it's worthwhile to have people have full-time jobs to take care of fires, right? So that's a recognized problem with combustion. Right now there's a big forest fire burning off of Los Angeles. That's another recognized thing, and actually there's people whose full-time job is to be firefighters and try to stop the forest from burning into the cities. But there's also new ones. Batteries also can light on fire, and you've probably saw some news stories about that. And they can be pretty devastating. And then we have to do hydrogen stuff. Hydrogen is like notorious as being very flammable. When we do a lot of electrification, we're going to get additional electrical hazards. So we have to worry about that. And biofuel and biomass, they burn too, just like fossil fuels, and they can cause all kinds of problems. And so we have a lot of problems that we already have today. Some of these problems are going to get amplified in the future. And then we have problems that we have today that we have to kind of get rid of and change the society to do something else. And so there's plenty of things to have to understand and how to change. And if you want to design a new system, it's best if you can think it through ahead of time and figure out what's really the good choice before people start making big investments to make the change. So as I said, I'm going to start by talking about this big picture. And then we'll get into a lot of details later in the week. So if you're not really into a big picture and you want to know about little atoms and stuff, I'll tell you about that plenty later. But right now, let's do the big picture. So today, more than 80% of all the energy that humans use comes from primary fuels. And the primary fuels, those are the raw materials that are readily available for humans to use. And so coal, petroleum, natural gas, biomass, those are fuels that humans have been using for more than 100 years, and we know how to use them pretty well, and we use them a lot, 80% of all the energy we use. Now, those primary fuels don't usually come in exactly the form that we actually want to use in our devices. So we process the primary fuels into some more practical fuel. So we convert them to what we call practical fuels, and things you heard about, gasoline, diesel fuel, jet fuel, pulverized coal, et cetera, the natural gas you burn to heat, probably to make the electricity in this building and to heat this building in the winter is not actually the natural gas you get from just digging a pipe in the ground. It's processed, and they take away the H2S, and they add some other stuff. But basically, it's the natural gas from under the ground, but they change it a little bit to make it the processed fuel. That's exactly what the burners expect here. We do have some kinds of energy we get without combustion, primarily right now from nuclear and from hydropower. And we get a tiny fraction of the energy from solar or wind energy. So we've heard a lot about solar energy, wind energy, and they're both very exciting technologies, but so far they're just a very small percentage of all the energy that humans use comes from them. Here's a picture of this over time. So you can see back in like 1800, people primarily used wood as the fuel source. So Princeton, if you look in all the old houses, have fireplaces, and people chop the wood and use the wood to heat the houses in the winter. Then by the middle of the 1800s, people started using coal a lot. They had a lot of steam engines. And then they discovered petroleum. By about 1920, 1930, petroleum became really big and grew through the 1950s and 60s. So you can see this pink part is petroleum. Natural gas came a little bit later. It became really big by about 1960s, 1970s. Most of the OECD countries switched to using natural gas as the primary fuel for heating houses. And then nuclear power came in also around the same time period. And there's already, hydropower had been used for a long time, but kind of small scale. And it got to be more and more industrialized, and really big dams were built. But you can see all of these things up to here are by combustion. So that's like more than 140,000 terawatt hours. And then we have maybe another 20,000 terawatt hours from everything else that's not combustion. So that's the reality of where the world is today. If you look at it on a pie chart, you can see that oil, coal, natural gas are by far the main energy sources. Biofuels are also pretty big, and then nuclear, hydro, and then everything else, which is mostly windmills, some solar cells. But it's only 2% of the total energy. So I distinguish between primary fuels and practical fuels. So practical fuels are materials that we make as humans to carry energy that's convenient for us to use. And mostly we do this through combustion. Primarily we convert that chemical energy into heat energy, and then with heat engines we might make something else. So you can run it some other way. So fuel cells and flow batteries work in a different way to make electricity directly. The fuels have much, much higher energy densities than other ways of carrying energy. And so this turns out to be super convenient. It's really easy to move huge amounts of energy all around the globe. So lots of energy is, for example, mined in Saudi Arabia and the Persian Gulf countries, and then that's shipped to countries all over the place. And it's not expensive to ship it. You put the liquid in a big ship, and you sail it, and it really doesn't cost much. And so therefore, the price of oil in Saudi Arabia is pretty much the world price, because the transportation cost is very, very small fraction of the cost. That's really convenient. It's also super convenient for transportation. So for example, on airplanes or ships, where you can't carry much weight of fuel, or you can't have much volume for fuel, then the high energy density fuels are really fantastic. And then usually we run chemical reactions to release the fuel, release the energy from the fuel. So, but every fuel undergoes different reactions, and they have different rates and make different products, and so this gets super complicated. And that's actually like my whole career has been trying to study all that kind of stuff. And the chemical details actually matter for the emissions, for how the engine operates, and so you have to worry about all these details, and that's why you guys are in this course. Here's some practical fuels. You guys have heard most of these. You have birthday candles, right? Thermite, if you ever did welding on railroad tracks. But there's a lot of the common fuels are up here. As I said, so about 80%, and then the 20% is from these. The petroleum, coal, and natural gas are separated from biomass and called fossil fuels. And the liquid fuels we use, almost 100% of them are made from petroleum. The fossil fuel means that it's a fuel that's formed very, very slowly, and it's a finite resource. However, it's a very large resource, so it's unlikely that we're actually going to run out of fossil fuels at any time. But in theory, it could be exhausted. And if the humans didn't dig it out of the ground, the fossil fuels would stay under the ground. And in fact, some of the fossil fuels have been under there for millions of years. But then when we dig it out of the ground and we burn it, we release the CO2 to the atmosphere. It's kind of very sudden on geological timescales. So we can very rapidly dig quite a lot of oil out. And in fact, in the United States, we have many petroleum reservoirs that are pretty much emptied because we've already taken all the petroleum out and burned it all. And that is a primary way we're increasing the greenhouse effect, by just dumping carbon that had been sequestered under the earth and bringing it up to the surface and burning it and letting it into the atmosphere. We burn a huge amount. So the total CO2 emissions, mostly from the fossil fuels, is this much. I can't even say what number that is. What's that? 40 billion megagrams. Megagrams like a ton. 40 billion tons per year of CO2 is being emitted from burning fossil fuels in the world. And most of this is for making electricity and for making heat. But we also use a significant amount for transportation and for other industrial processes besides heat. Coal and natural gas are the main fuels for making the electricity industry and for heating. So they're actually responsible for most of the CO2 emissions, but most of the money, the economic cost, is in transportation, because they're made from petroleum, and petroleum is more expensive than coal or natural gas. And we use quite a lot of petroleum too. So about 100 million barrels of petroleum are burned every day, or consumed every day. Not all burned, but most of it's burned. And so if you take that today's price, about $80 per barrel, you multiply that all out, it turns out to be about 3 times 10 to the 12 dollars per year just to buy the petroleum. So that's about more than $300 per person on Earth per year just for the petroleum. And that doesn't count the cost of all the other fuels. It doesn't count the cost of the equipment that was used to burn the petroleum, all the vehicles and everything. It's just for the fuel itself. Actually, just for the primary fuel. It doesn't include the cost of refining it into the finished fuels. So it's a lot of money. In many countries on the Earth, $300 per year is actually like close to the total average income. And so this is serious money. If you look at what the greenhouse gases are coming from, a lot of it's from making electricity and industry. So these are really big. And then heat for buildings is a little sliver here, still significant. And then transportation, that's all the cars, trucks, airplanes, is also pretty significant, but smaller than the other one. And this yellow band is all about land use, agriculture, forestry, deforestation, everything about land uses. That's also pretty significant. But the biggest ones are the blue, green, gray, and red, and those are all essentially all combustion of fossil fuels. And you can see the CO2 is rising. So this is the measurements of CO2 with time at the same place, and you can see it just goes up, 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 up. This number, this plot stops at 2019, I think. Now it's up to 420 ppm. And you can just, it matches exactly what you expect by how much fossil fuel is being burned, and then you measure how much CO2 is in the atmosphere. We have material balance. So it's very well known what's happening there. A certain fraction of the CO2 dissolves into the ocean. That's also been measured, so the whole thing balances out. Historically, back in geological time, there's a near perfect correlation of the amount of CO2 in the atmosphere and the global temperature, as would be expected if you did the greenhouse gas calculation. So the blue here is the temperature, and the green is the CO2. And you can see just perfect correlation. So there's really no doubt that when the CO2 level goes up, as we're making it go up now, the temperature is also going to go up. Some error bar exactly what the number of the temperature is, but it's going up, matching going up. There's no doubt about that. And I mentioned this before, but I'll say it a different way. In the total greenhouse gas problem, from all the things humans are doing that's putting greenhouse gases in the atmosphere, about 2/3 of it is CO2 from burning fossil fuels. We also have some significant amount from land use changes. For example, when they chop down forests to make more farms, the carbon that was in those trees is then emitted, and that's an important thing. And then this nitrous oxide is really important too, and this is from fertilizers. We put nitrogen fertilizers in, which we have to do for the plants to grow, but there's some bacteria that convert our fertilizers into N2O, and the N2O is emitted. N2O is a very strong greenhouse gas, so that's also a significant amount. And then there's like freons that we use in refrigerants and stuff like that, and they also have emissions. But that's not all our problem. We're in the combustion community. We're just responsible for 2/3 of the problem. The other people, the agriculture people and stuff, they can worry about the other 1/3. We have enough problems, I have to tell you. You have to understand the carbon cycle to understand this whole distinction between fossil fuels and biofuels. The carbon and nitrogen atoms that are in the biosphere, that's in the surface of the Earth, in the surface waters of the ocean, in the atmosphere, they all interchange really fast, with a time scale about a year. And so that area, that's treated as sort of as in quasi-steady state, partially equilibrated, is all the carbon. Some of the carbon's in the form of like decaying plant matter, some is in live plants, some is in CO2 in the air, some's in fossil fuels that we have in our ships. All that kind of stuff is all in the biosphere. And then there's the surface ocean is in equilibrium with the atmosphere, but the ocean's very deep. And the bottom part of the ocean is not in good transport contact with the atmosphere. It's down there for like 1,000 years. So once the waters sink down to the bottom, they stay down there for a long time, but eventually there's an upwelling and they come back up. And that time scale is about 1,000 years. And then we have the very slow time constant on the land between the surface soils, which are in good contact with the air. If you go down a few hundred meters, now you're completely out of contact. And the stuff is, the rocks and stuff are not in equilibrium with the air at all. A lot of them are still reduced forms. They haven't been oxidized because they haven't seen the oxygen from the air. And in fact, the carbon, say coal down there, equilibrium would be the coal would react with the oxygen from the air to make CO2, but it's still coal. And that's because the transport is so slow through the solid. Diffusion through solids is really, really slow, so that the oxygen from the air has not been able to make it down there to where the coal is. So the coal's been sitting there about 300 million years. So it was trees back in the Pennsylvanian period. There's a lot of trees on the earth, and a bunch of them decayed and got buried and didn't ever react with the oxygen, and they got sunk down deeper and deeper, and they became all the coal beds that we have. And this is a commentary maybe about sequestration, too, that it's definitely possible for things to go under the earth and then be down there for what's basically forever on a human time scale. And so that's the idea of carbon dioxide sequestration, is that you could bury the CO2, and if you did it properly, maybe you can get it just like the coal stays down there. Of course, it's also possible things come up, right? We have volcanoes, we have geysers, the stuff comes up from down below too. So it's not like 100% sure, but on average, stuff that's buried deep under there stays under there a long time. So pre-modern era, the things in the biosphere, like including CO2, were all in quasi-steady state with each other. The plants absorbed the CO2 and grew. Then when they died, the plant carbon decayed and it went back to CO2. And then humans changed it. First we did land use changes. So for example, Britain used to be all forested, and now it's basically all grass because people chopped down all the trees. In other places, like in the Sahel, the Sahara actually used to be pretty forested, and now it's a big desert, and the Sahel region used to be forested as well, and now it's basically just scrubland because of a lot to do with what humans did. And so that shifts the carbon from the carbon was existing on the earth in the form of the plants, and now it decayed away and it got released to the atmosphere as CO2. Now, if we take that dead biomass, say a stick falls down the ground, and we convert it to a biofuel and use it to run our car, that's similar to what's going to happen anyway, because the microorganisms are going to decay the stick and make it into CO2. But if we do it in our industrial plant, we'll probably do it faster than the microorganisms would do it. So the stick would become the biofuel, we would sell the biofuel, we'd burn it, and the CO2 would go up, and it might go up a couple years faster than it would have done naturally by the decay process. So when we use biofuels, we're not getting more fossil carbon out from under the earth. So in that respect, we're doing better for the atmosphere. But we're not exactly doing the natural process because we're kind of accelerating it because we want the fuel now, whereas the bacteria are more slow about how fast they would convert the fuel into CO2. So you get a modest shift in the steady state and a kind of a small net greenhouse effect from using biofuels. Figure out exactly how much that shift is kind of complicated, but some people work on that. And historically, in the modern era, humans have taken many billions of tons of carbon from subsurface and dumped it into the biosphere. And that's increased, basically, that's the main reason that the increase has happened from 270 ppm. Now it's actually 425 ppm today. All right, so what's the problems with the current energy system? First one is that fossil fuel combustion is the primary cause of climate change. There's a secondary problem that might be more apparent now when there's so many wars going on around the world and so many international tensions, is that petroleum in particular is very unevenly distributed around the world. And that leads to fears of blockades, embargoes, all kinds of energy security concerns. And this is definitely like an undercurrent between relations, say, of India and China with other countries, is that those countries don't have nearly enough petroleum resources to match the needs of their population. So they have to import quite a lot of petroleum so people in those countries would be able to use vehicles. And so that's definitely on the minds of the people in charge of the defense departments of those countries about it. And particularly in the previous century, the World War I and World War II were both largely decided by blockades. And so it's definitely a thing that people think of as can be a very important thing. Another important thing is price. And we've had since like 1974, I think, 1973, there's been a cartel that's controlled the price of petroleum and made it much higher than what its natural economic price would be. And so that has different pros and cons. So one is, to the extent that the cartel holds the price steady, that's actually really good for the economy, because it makes it easy to calculate, if you make some kind of device, what your price is going to be in the future to operate the device. However, the cartel doesn't always keep it steady. And so we've actually had a couple wild swings in the oil price. And that's occasionally the price has gotten so high that it's caused the world economy to go into recession. So the last time that happened was like 2008, 2009. Oil price got up to $140 a barrel. And there was called the Great Recession, all worldwide. And there was kind of several similar things happened in previous years. And then there's another problem that's maybe very much on the mind in some places in the world. So for example, in Delhi, at certain times of the year, the air pollution is terrible. And what's happening there is that people are combusting, actually in that case, mostly biomass. And the plume from those fires is going over Delhi and making it really dangerous for people to breathe. In previous years, this happened famously in Beijing. Before that, it was very famous in this country, in Los Angeles. Before that, the London fog. There was a thing called the London fog, which was actually like the smog of death. Killed like more than 100 people in London one time. So all the countries of the world have had this. I think Paris had this episode maybe 15 years ago. So there's been periodically episodes where the local air pollution got so bad that it was obviously damaging human health. And in fact, many of the combustion innovations that you guys work on and the people you work on are all related to this problem, the local air pollution problem, smog and particulates. Because of the climate change one, there's a lot of interest in non-fossil energy sources. So that's one big thrust of research recently, is trying to figure out how can we get the energy we need without using fossil fuels. Because of energy security, there's a lot of interest in non-petroleum fuels. They're not exactly the same. The security concern is primarily about petroleum because that's the most maldistributed resource. Most of the big countries have a lot of coal and so could supply their own energy needs from coal if they needed to, except it's hard to make coal into a liquid to run cars. So they can't meet their need for transportation very easily. So these are partially overlapping because petroleum is a very big fossil fuel, but they're not 100% the same thing. And then another problem is smog, and primarily that's been controlled by emission control systems. So in many countries, cars must have catalytic converters to try to control the smog emissions from the cars. Modern trucks have to have particulate filters to try to reduce the particulates. There's certain devices you put in coal power plants to try to control the emissions from the coal power plants. So there's been a lot of work, and this community is in part of that, of trying to figure out how to do combustion in a way that there's not local air pollution. Now, there's still many places in the world where there is local air pollution from combustion. And even in rich countries, there's some kinds of devices that are not regulated, and they still pollute like crazy. But primarily, this has been the main way that problem's been dealt with. Recently, people have also thought, well, maybe we can switch just to electrical as a way to try to control the local air pollution. And in some places, that's a popular strategy, too. OK. Quiz question 1. You guys ready? All right. So the carbon dioxide you get from burning a fossil fuel is not very different from the carbon dioxide you get from burning another fuel. So why do we bother to distinguish between fossil fuels and other biofuels. They both make carbon dioxide. The carbon dioxide goes up in the air and causes the greenhouse effect. Why do we think it's a big deal to call some fossil fuels and some not? Yeah.
Accelerating it because we need the fuel right now. So that's adding carbon quickly to the atmosphere, and so we care about it.
Right, and certainly compared to the fossil fuel timescale, way quickly. So it may take millions of years for the fossil fuels to go down, and we can bring them up in 1 year. And so it's 1 million times faster. With the biofuels, there's a similar thing, but it's a much more similar timescale that the normal decay might be a year or two, and the human accelerated thing might be a few months. And so it's maybe a factor of 5 or 10 faster, but not a factor of 1 million. Yeah. All right. Now, a sad but true thing is that we're going to run out of atmosphere before we run out of carbon. So we have quite a lot of fossil fuels under the ground. And the climate scientists have calculated how much of that carbon we could actually put into the atmosphere before we'd have like devastating climate change. And so there's numbers, and I don't know the numbers myself, but you can look up the IPCC reports, and they say if you put this much CO2 up there, the climate's going to change by 5 or 6 degrees, and basically Antarctica is starting to melt. We're all going to be underwater. It's total devastation, right? So there's some number. So you don't want to emit that much CO2, right? Because that would be really bad, unless you're really good at swimming and treading water. And the numbers have been checked by essentially all the governments in the world. And that's why the Paris Agreement was signed. It was basically all the governments double-checked the numbers, and they agreed, yep, that's right. We can't put that much CO2 up there, or we're going to be in deep doo-doo. All right? Now, separately, the fuel companies have identified a certain amount of carbon that's available to them under the earth, coal and natural gas and oil. And if you add up those numbers, they report them as their proven reserve. So if I'm the head of an oil company, I own the mineral rights for some piece of land, I carefully measure under that land, I see how much carbon's there, I report to my stockholders, hey, you guys should be proud, our company owns the rights to however many million tons of nice fuel, we're going to be able to sell it, make lots of money, we'll be able to pay you nice dividends on your stock, right? So they report this number, every quarterly report, there's a proven reserves number they report. The sad thing is, if you add up those proven reserve numbers, it's bigger than the number that the climate scientists say we could emit. So there's like some contradiction here, because either we're going to actually use those proven reserves, in which case the stock people are getting what was promised by the company, but the climate will be destroyed, or a lot of investors who bought the stock are going to lose a lot of money because the company owns that carbon under the ground, but they're never going to be able to produce it, because if they did, it would destroy the climate. So somebody's going to stop them. But right now, we have these two ideas in tension, unresolved. So the stock prices for companies that own a lot of carbon under the ground is very high, and we all agree that we can't put all that carbon in the atmosphere. I don't know how it's going to get resolved. And I think this is a very important fact to keep in mind in general in dealing with this problem, is that humans are inconsistent. We're not a bunch of math equations. We don't always do the most sensible thing. And so if you talk to most people in all countries in the world, they would be very happy if the climate didn't get screwed up. There's a consensus. The Paris Agreement, it's not like nobody forced the government leaders to sign that agreement. They were reflecting the true views of people in their countries, that basically the majority of people don't want the climate to be screwed up. There's a definite agreement. But also, if you ask people if they want to go to vacation, they want to get an airplane and fly there, that's what they want to do, right? And the implicit contradiction between these two desires has not really been resolved. Same with electricity. Everybody loves to use electricity, right? We all like to play video games. We all like to use AI to generate fun sonnets for us, or funny limericks, or whatever we're doing with AI, and do complicated computational fluid dynamics calculations. Whatever you're doing, you like to use electricity, use the lights in our building so we can see each other, right? So we're all happy to do this stuff. And in fact, certainly I and all the older people in this room probably own stocks in, in their 401k, their pension or something. And a lot of that money is actually invested in the companies that supply both the fuels and also the vehicles and stuff that is based on those fuels. And so we're investing in that ourselves for our retirement funds. Okay, so it's like completely contradictory all the way around. And I think this is just the reality. It's like I don't think I apply evil intent to anybody. It's just people intrinsically are inconsistent. But it's a big problem if we all act like all these things can be true at the same time when they cannot, right? And in society, the engineers and the scientists are the people that everyone else looks to tell them the true story and how we're going to really solve the problem. So it's on us in this room to present part of the solution and then to help the society come to realize, like, oh, we actually have to change and we actually have to do something, and here's something practical we really can do. Until a practical option is offered, no one's going to do anything. So that's the situation. Okay, a few more just general comments about fuels. First thing is, it would be great if all fuels were liquids. Liquids are by far the best fuels. They're energy dense, they pour. You can just hold them in a bucket. You don't need to have a pressurized gas cylinder or anything to hold them. There's no solid to handle. You don't have to worry about dust or particulates from the stuff. You don't have gunk clogging up your pipes. Just nice, beautiful liquid. But because they're liquid, and they're the best, they're also the most expensive. So, for example, the OPEC cartel has been able to raise the price a lot. It's much, much higher energy cost per joule for petroleum than it is for other fuels. But people are happy to pay that premium because they get a better fuel. They get the fuel they want. That's the first thing. And so, for example, transportation, almost everybody doing transportation pays for liquid fuels. People tried before. Ships used to use coal. They had guys in the basement, in the bottom of the ship, who were digging the coal and shoving it into the boilers. And at the moment they could, everybody switched over to oil instead. Second thing is that price really does matter. And because the price matters, people do not use petroleum for a lot of things. They don't use petroleum very often to make electricity. They don't use petroleum for heat. They don't use it for most industrial processes. And that's because it's cheaper. And instead they use coal or they use natural gas primarily, depending on which one is cheap where they are. So this is a kind of a problem for us as engineers if we're proposing solutions that we need to find a solution that can be kind of cost competitive or comparable to coal or natural gas. And that's a much bigger challenge than finding something that's comparable to petroleum. Petroleum is pretty expensive. You could think of a lot of things that have similar prices to petroleum. But it's really hard to find things in this country cheaper than natural gas is like almost impossible. And in some other countries like China, cheaper than coal, really hard to beat coal. Now we have some ideas about this. One thing that's a really great innovations recently is people figured out how to make really efficient windmills and photovoltaic cells so that the cost of electricity from wind and solar is now cost comparable to electricity from coal or natural gas. So you can see even in China where coal is very cheap, they have building lots and lots of solar cells because it actually is cost competitive with the coal. In this country, we have natural gas that's very cheap. We're still building lots of windmills. We have a lot of wind, and the windmills are actually cost competitive to the natural gas. So because of that cost competitiveness, the renewables are winning market share, and it doesn't take much government policy or subsidy to persuade the electric companies to switch over and to install some solar cells and to install some windmills. Similarly, heating buildings, it turns out that a heat pump run on electricity has comparable operating costs to heating with natural gas in this country, and probably the other countries too. And so because of that, heat pumps are starting to come in and grab market share. And the heat pumps work best when the delta T is not too large between the outside air temperature and the inside. So in this country, heat pumps have been very successful in the south because even on the coldest days, it doesn't get that cold. And so the heat pumps are actually really efficient. And so that they've been super popular. And they're starting to grab some market share up in the farther in the north as the technology improves. But we don't really have any cost comparable options for industrial heat yet. And so this is a big challenge because this turns out to be a lot of energy, a lot of CO2 is from this combustion. How could we possibly solve that problem? You can use electricity, and in fact, you'll see some governments are promoting the idea to use electricity to replace industrial heat. But you have to keep in mind, we normally run this in the reverse direction, where we take fuels, we burn them to make electricity. That process is pretty inefficient. So it's for maybe 40% efficient. And so that means we use 2.5 times as much fossil fuel energy to make a certain amount of electrical energy. So the price difference is electrical energy is like twice as expensive, at least twice as expensive as fossil fuel energy. And then if you have to transmit the electricity from somewhere, you also have to pay for the wires. And so it turns out to be pretty expensive. In some places and sometimes the wind and solar can get quite cheap, and particularly if it's close to the plant, you don't have to ship it very far. But then you have to deal with a variability issue that a lot of the industrial processes we have now are set up to run continuously exactly the same way, 24/7. But if you have a variable source of heat, you have a problem that it's like varying up and down, but you want to take the same amount of energy all the time. So that's another issue with electricity. Now, one way around this is to switch your process. So you could try to run a process electrochemically instead, and that actually avoids some of the energy losses, and you potentially could do a lot better. But that technology is not that well developed yet. So there's like a lot of people are doing research now on electrochemical ways to run industrial processes. Another way is to try to use hydrogen to replace the fossil fuel. And you can make hydrogen from coal or natural gas, but whenever you do a conversion, you lose some efficiency. So the hydrogen energy you make from natural gas or from coal is more expensive than the native natural gas or coal energy. And then if you make the hydrogen from electricity, it's going to be at least twice as expensive as that other hydrogen. And also, if you try to use hydrogen directly, it's a gas, so you need a gas pipeline. And in hydrogen embrittles certain common materials, so you have to use special materials too. So it's a little bit of a pain, but you could do it if you can run a pipeline from where you make the hydrogen to where you're going to use it. So then people said, well, maybe instead of using hydrogen as a gas, we could make a fuel out of hydrogen, make a liquid. Then we could ship it all around the world. That would be really great. We can store it. That would deal with the variability problem because you could have a tank of this liquid at your factory. And so, for example, if the windmills weren't making electricity at some time, you could just use the liquid. That would be really great. But it's going to be more expensive because you have to first make the hydrogen, and then you have to do some conversion process to make it to the liquid. So it's going to be more expensive. And I think fundamentally my conclusion about this right now is we don't have a technology that can really beat industrial heat. And so we're going to need a carbon policy from the governments to encourage the companies to switch because economics alone are not going to make the switch. So it's going to have to be some policy. And the key is trying to figure out practical solutions with a clear cost that you could communicate to the government policy people and say, look, if you would only make a carbon tax this high, if you would only make a policy this way, that would be enough to get the industry to change, and it would not impose an onerous cost on the industry or on the customers of the industry. And so that's the challenge ahead of us in the industrial heat world. Another very important thing to keep in mind is that in most applications, the energy is not the biggest cost. So if you're doing, playing video games, it's not the electricity you use to play the video game. It's the cost of the Xbox or whatever the heck, equipment you had is most of the cost. In transportation, it's the cost of the vehicle, it's the cost of the labor, of the drivers. That's the cost. The cost of the fuel is not the main cost. So for example, the airlines really don't want to switch They want to use the nice airplanes they have, and they want some new clean fuel to arrive and just go right into their old airplane, so they don't have to spend $100 million to buy a new airplane. So this difference in the different sectors, it's all different, but almost every sector, the energy cost is not the dominant cost. Now this is also kind of good because it means that the government policy, if they raise the cost of energy, for most final products, it won't change the cost that much because the cost of the final product is mostly dominated by the capital cost and the labor cost, and the cost of the energy is only a few percent. So even if they doubled the energy cost, it would only go up a few percent. And so industry is the same, particularly like a chemical plant. Those things are just massive amounts of capital. There's no way somebody wants to shut down a chemical plant and replace it with something else. They just want to keep operating it. Maybe they'll make little tweaks to use a new fuel or something, but not much. Same with buildings, actually. I own a house. The value of my house is much, much more than the value of all the fuel I ever burned in my house. And so to me, it's like the fuel is like a minor percentage, less than the property taxes. It's really like not even in the calculation economically. So that the situation like that where the owner of the asset doesn't see the energy as being important is kind of bad for making a transition because there's like no incentive for them to spend a lot of time on it because everything's working fine the way it is. I don't care if the price doubles, who cares? It's only a few percent of my total cost. Right? So that's a very important thing psychologically, but it's real. It's not just a thing. It's from the total cost, the value of this building is completely unrelated to the cost of how much it costs to run the lights. Right? You're still going to turn lights on, no matter what the price is. When people come here, they want to be in the lights. They don't want to stay in the dark, so they're going to turn the lights on. Right? All right. Part 2. So I'm going to talk now about transportation in particular. This is a chart that shows how much energy density matters. These are for ships. And so, for example, this is the Emma Maersk. It's a big container ship run by the Maersk company. Is this blue line. It shows that if you switch the fuel from today, it's using a bunker fuel. It's basically petroleum. And you switch it to a fuel that had, say, 3 times as much weight, you're going to decrease the payload by about 40%. So that means that all the money that they make from driving that ship around is going to go down by 40% because they use the payload to carry fuel instead of carrying goods. But the purpose of the ship is to carry goods, not to carry fuel, right? That's why they have all the sailors and the captains, and why they made this big ship is to try to carry a lot of goods. And so that's a really big financial loss for them. And so for most ships, they can't afford to have fuels that are much heavier or take up much more volume than the fuels they use today. Similarly, you can do the same analysis for jets. And basically, when you do this analysis for jets, you find out that only hydrocarbons can work for jet airplanes to do transoceanic flights. If you switch to heavier fuels, you'll have to stop. So in the old days, they used to stop in like Newfoundland and then stop in Ireland in order to get to Europe. You'd have to fly like that if you're using heavier fuels. So jet fuel is like great because it allows you to fly all the way to to Warsaw from New Jersey in one shot. That would not be possible if you had heavier fuels. Ships, there's a couple options. You could use hydrocarbons as we do today. You could use alcohols. You could use liquid hydrogen. You could use ammonia. But that's about it. There's no other substances known that have high enough energy densities that you could use in a ship. For trucks, there's a bunch of different options. It's not quite as difficult, but there's a lot of practical issues with the trucks because it's retail, not wholesale for the trucks. There's this famous plot that shows different options of the energy carriers and how much specific energy they have, is like how much energy per kilogram. And you can see the liquid hydrocarbons are here. They're way at the right-hand side. And then batteries are in here. It doesn't look that far apart, but this is a log plot. So it's more than a factor of 10 difference between the energy densities of liquid fuels and the energy densities of batteries. And so that's the fundamental problem with batteries is they're just really heavy and they don't carry that much energy. They're actually really expensive too for the amount of energy they carry. In other respects, they're great, right? There's no local pollution from a battery. The cars are great. They have great performance because they have a lot of power. But it's really a problem with energy density. And people tried a lot of things, flywheels and supercapacitors and many, many different ideas. But fundamentally, basically, you need a liquid to do it. So what do we want in a transportation fuel? We need the energy density. To help with energy density, we prefer not to have to carry more than one reactant. So typically, we carry a fuel that's a reducing agent, and then we take the air from the atmosphere, take the oxygen, and react it with the fuel. And we can't take the nitrogen from the air because we don't have anything that reacts with nitrogen. We definitely can't take the argon from the air because it's only 1%, and we don't have anything that reacts with argon either. So the only thing we can react with is the oxygen. So we need to find fuels that have very highly exothermic reaction with oxygen. And we need the fuel to be super abundant in nature because we're going to use millions of tons of this stuff every day. And we need to be super cheap. And then ideally, the fuel itself should be safe and it should be environmentally benign because if you have millions of tons of anything, a percent of it's going to leak. And that's going to be 10,000 tons, right? So it's not like a small leak. So you have to figure out, find fuels that are benign enough that you wouldn't get too agitated if you have 10,000 tons of it leaking. You prefer to dump the product as exhaust so you don't have to carry its weight, but that's just not 100% necessary. You want the product of the reaction also to be environmentally benign because we're going to make millions of tons of that stuff too. So we need that to be good. And we prefer that both the fuel and the exhaust be liquids or gases. We don't want to handle any solids because solids just gum things up and clog things and are a problem to handle. So liquid fuels are way preferred. So what we can use to make a fuel, all we've got is the periodic table. So we can look at every single element in the periodic table. And we can say, well, what gravimetric energy density do we need? So we can do the calculation and say, well, if we want the mass of the fuel in a car to be less than 100 kilograms, then we need about 10 kilojoules per gram heat release from reacting with oxygen. And so here you can look at all the elements that have that number, and it's only these guys that are colored. So we crossed out most of the periodic table as not reacting exothermically enough with oxygen. Then you can also say we don't want solids, so that we don't want the product of oxidation to be a solid, and that just leaves these guys. And if we do the intersection of these two, we're left with two elements. So now you know why, the real reason why we use hydrocarbons. It's not just because Exxon or General Motors tricked everybody once or something. It's just that that's the only two elements that work, that have a high enough energy density and don't make solid oxide products. You can actually include oxygen in the fuel. It doesn't help you, but it doesn't really hurt you. It just makes the fuel heavier. It doesn't give you any more energy, but if you can afford a little bit lower energy density, it's okay. You can also do it with nitrogen. Nitrogen, you say, well, that's kind of bad because it's going to burn to make NOx, which is a notorious local pollutant. But we actually have pretty good technology for getting rid of NOx now. So you could actually include some nitrogen if you wanted to. Nitrogen is not that great, though, because the nitrogen-rich fuels are toxic, like pretty toxic, like really toxic. So that's a problem. All right, so we decided we have to stick to fuels that are based on carbon and hydrogen, maybe some oxygen and nitrogen. Everything else is no good. And we need the high energy density. And we'd really like it to be a liquid down to like -20 C, so truck drivers in Finland are not going to die in the winter because all their fuel freezes. And we need some good volumetric energy density too, so that kind of rules out hydrogen. So basically, we're stuck with carbon. And therefore, we're stuck with CO2 as the main product. So this is really a negative analysis. Basically says we're doomed. And what are we going to do? So we have to relax one of the criteria, at least one of the criteria I mentioned before. So let's take a break now, and then when we pick up, we can talk about which one you guys want to relax. Thanks.